Great. Thanks so much, Emily. And thank you for this honor. I'm pleased to be presenting today. I am calling in from San Francisco. So wherever you may be, I wish we could be together in person, but it's nice that we can reach across the continent to talk about these topics. I'm going to share my screen here. And hopefully you'll be able to see this.
Looks great.
Okay, great. So when climate and energy collide is the topic today, and I'm just going to jump into it without further ado. So we know that we are already experiencing the impacts of climate change. We know this from our personal experience, from reading the news, as well as from science and the scientific reports from the Intergovernmental Panel on Climate Change. But just to orient us and ground us all in the same reality. Across the top, you'll see some of the impacts of climate change that are pretty well understood at this point. And when I first started working with the Aspen Global Climate Institute to prepare for this workshop that this lecture is part of, it was back in February when the winter storms had just hit Texas and led to power outages across the state. About 70% of Texans lost their power during that winter storm. Fast forward to this summer, we saw massive heat waves hitting the Pacific Northwest, tragically leading to deaths, as well as blackouts of the electric power grid. And the loss of air conditioning associated with those blackouts contribute to public health and safety concerns, of course. And then, just earlier this fall, we saw Hurricane Ida slamming into Louisiana, causing power outages there for over a week in extremely hot temperatures. And the overall conclusion is pretty clear that climate change is happening and we are not ready. So what do we need to do to slow the impacts of climate change? Well, we can look to the recent Climate Change 2021 report from the Intergovernmental Panel on Climate Change. So we know the scientists are telling us that we're already experiencing the impacts of climate change. We've seen about 1 degree Celsius warming relative to just 1 generation ago. Another way of looking at that is what are our emissions today? We know they've increased over time, and now as a globe, we're spewing about 35 to 40 gigatons of carbon dioxide into the atmosphere every year, as well as a range of other greenhouse gas emissions. And the question is, which one of these lines are we going to be on as we move forward? We want to be on this light blue line, not on the red lines. The red lines are the trajectory that we appear to be on, but there is an opportunity to change that future. And if we can get within spitting distance of a net negative or carbon neutral future by mid-century, that will give us the best chance of staying within a 1.5 degree sea warming future by mid-century. So even in the best case scenario, and it truly is going to be a massive undertaking to achieve carbon neutrality by mid-century, we're still expected to see at least another 0.5 degree of warming, which will intensify the climate impacts that we are already experiencing. So stepping back from the global perspective to think about the US for a moment, what would it take for the US to achieve net zero greenhouse gas emissions by mid-century? This is the goal that the gauntlet that the climate scientists have thrown before us. And it's a policy goal of the current administration as well. But it's a It's a daunting task. It will require emission reductions from all sectors of the economy. So this figure shows greenhouse gas emissions today on the left in 2020 by sector. And you can see that the electric generation sector and the transportation sector represent the largest sources of emissions in the country. We have natural and working lands that are actually sucking carbon dioxide out of the atmosphere and representing a carbon sink. So the net greenhouse gas emissions are the difference between those gross emissions and the carbon sinks. So in order to get to a 50% reduction below 2005 levels in a decade, and to get to net zero by 2050, we know that the electric generation sector is going to need to shoulder a large portion of that burden. And you can see in this figure that it's that top blue wedge that's almost reducing to zero within the next 10 to 15 years in order to enable carbon reductions in other sectors through electrification. But no sector here is getting a free pass. So we can dive in a little bit more into detail about some of the actions and strategies that would be required in each of those sectors. And I won't go through each of these because our talk today is focused on the electric generation sector. But in brief, we know that we will need coal retirements. We know that we'll need massive expansion of renewable generation, as well as new transmission to interconnect that generation to loads. And we'll need energy storage to help balance supply and demand. We know that we'll need electrification in the transportation sector. As much as 100% of all sales of light-duty vehicles by 2035 would need to be electric in order to be on pace to meet the carbon neutrality goals. And this is in part just because the turnover of our stock of vehicles is relatively slow. And so even if we get to 100% electric sales, we'll still have a large number of conventional vehicles on the road, even for the next 15 to 20 years after that. So moving on, another way we can think about these emission reduction strategies is to group them into what we call pillars. And these 5 pillars we see consistently showing up when we look at greenhouse gas reduction opportunities in different states. Other researchers have found similar strategies being necessary in other countries. So these are really the tools in our toolbox to reduce emissions. And these include, of course, energy efficiency and conservation across all sectors. It includes electrification in primarily vehicles and buildings, but also to some degree in the industrial sector. Low carbon electricity, I already mentioned, is an essential strategy here. This is mostly in the US going to be renewables with storage and hydroelectric generation, but it may also include some nuclear and generation with carbon capture and storage, particularly in countries that have less access to renewable generation. We know we'll also need low carbon fuels for those sources and equipment that are difficult to electrify. That includes things like biofuels and hydrogen. And finally, we'll need to sequester carbon and reduce our non-combustion greenhouse gas emissions. So how does climate change impact those decarbonization strategies that I just described? We can put together a very similar table, breaking it down by sector. And this time in the boxes, you'll see climate impacts and adaptation needs. So in the electric sector, we know that electric reliability risks are already happening, and those are coming from flooding, storms, wildfire, and heat. We know that heat degrades equipment performance. We know that drought lowers our access to hydroelectric generation. And we know that changing generation profiles from wind and solar are expected from things like smoke that can obscure solar panels. And so there's a lot of moving parts here, but as we decarbonize our economy, the transportation sector, the building sector, the industrial sector become increasingly impacted by these climate impacts. Another codependency between these sectors that I can point out that's relevant from just the storms that we saw hit Texas, some of the power outages that they experienced were a result of a natural gas infrastructure freezing, meaning that natural gas generation wasn't available to produce electricity. So the climate impacts can be confounding across sectors. Now, digging in a little more deeply into the electric sector, there's these two factors that we're trying to plan for. Electric sector decarbonization, and then climate impacts. So how can climate science better inform our electric sector planning? Well, we know that the electric sector is pivotal to reducing greenhouse gas emissions. This figure here is also from our modeling work around a US scenario that achieves net zero greenhouse gas emissions by 2050. And in this scenario, you can see that electricity demand is increasing 150% in this scenario relative to today's levels due to electrification in buildings, in transportation, as well as increased electricity demand to produce hydrogen, which is a zero carbon fuel if produced from renewable or zero carbon electricity through electrolysis. So planning for this growth and expansion is one of the tasks ahead. The other is decarbonizing the electric sector, and that requires increasing the share of zero carbon electricity that is being served. We did a literature review across a range of studies that look at deep decarbonization and net zero in the United States. And we see these ranges of wind and solar as a share of total electric generation. Today, about 10%, slightly under 10% of our electricity generation in the US is coming from wind and solar. And in a scenario that achieves an 80% reduction in emissions by 2050, that range looks more like 45 to 55%. But in a net zero scenario, we need more like 70 to 90% of our generation coming from wind and solar, with the remaining 10 to 30% coming from other forms of zero carbon generation. So we're both expanding the footprint of the electricity sector, as well as completely changing the generation assets that are producing power to power that grid. So how do we do this planning? I won't get too deep into the governance and planning in the electric sector, other than to point out that it's a pretty distributed affair. Electric planning is mostly done by electric utilities, which you can see across those three maps in the top. We have a range of investor-owned utilities, publicly owned utilities, and electric cooperatives in the United States. Electric reliability planning is also done by balancing authorities, of which there are about 66 in the United States, and that's across three main transmission interconnections. But there's a lot of power actually at the balancing authority level. And then to some degree, we also have electric reliability assessment checks within NERC, these North American Electric Reliability Regions, of which there's about 20. So even at the most aggregated level, that 20 different NERC reliability assessment regions, it's still a pretty distributed governance when we think about this type of planning challenge. So a little bit about how we plan in the electric sector, and I hope this isn't getting too deep into the weeds, but in the past, the planning paradigm was really driven by planning for peak demand. And that was, mostly a question of, do we build, a nuclear facility, a coal facility, or a gas facility? And it was a relatively straightforward challenge. Today, we're dealing with a different system where chronological and hourly generation and loads matter a lot more. And we're looking at the net peak, which is not just peak electricity demands, but what is the timing and correlation of peak demands with variable renewable resources. So this requires a little bit more sophistication in our planning paradigm. But looking forward, it becomes even more complex as we look to remove or replace some of those baseload resources and match variable renewable generation resources to changing hourly electricity load profiles. And to do this well, we're going to need a lot more resolution at the spatial and temporal level. And we're solving for different types of problems. It's no longer a peak demand issue that may last a few hours, but the reliability challenge becomes something that in German they refer to as the Dunkelflaute, and that translates in English to something like the doldrums, which is what do you do when you have very low renewable generation periods that span multiple days and potentially high electricity demands. We need energy storage, load shifting, and load management strategies to address that. Another challenge in that ties into the climate impacts is, what happens to peak electricity demand? We typically use extensive records of historical weather in order to simulate loads. Electric reliability planning ideally requires these weather match data sets so we can have a correlation between peak demand and renewable generation outputs. And we see, quite a range in the extreme peak demands, but that's, before accounting for future climate impacts. So that is to say that there's this emerging challenge around, how do we reflect future impacts in terms of both capturing how the average weather changes as well as the frequency of extreme weather events and how that might change the peak periods that we need to plan for. Now, of course, the generation side is changing as well. We at E3 use data from NREL to simulate very granular spatial and temporal wind and solar generation, but this data does not yet reflect the future impacts of climate change. Another impact on the generation system from climate change is the degradation of the efficiency of the equipment. As temperatures increase, we see up to a 20% reduction in output relative to the design rating. And many electric planning tools don't yet capture this effect or have a sophisticated way to even forecast what that might look like. So what's a way forward here? The goal, of course, is to improve on the status quo. And today there's been a lot of focus around just properly characterizing the joint probability of load and renewables with today's climate and historical weather. We could improve that by adjusting even for just the historical changes that we've seen in the last 10 years due to climate change. Even better than that would be a better characterization of the uncertainty and future climate impacts on loads. And even better than that would be taking into account both the changes in the loads as well as the changes in generation in a more dynamic reflection of climate impacts. So, we're trying to balance these multiple priorities. There's a long-standing kind of framework in the electric sector world that we're planning for a safe, reliable, and affordable energy system. And we can think about safe in many ways. Traditionally safe has meant public safety, but it can also mean, climate safe, environmentally safe. And equitable and affordable, of course, means that we can't spend so much money improving the reliability of our electric grid or reducing carbon emissions from the electric grid that we can no longer provide electricity to the poorest members of our society. We need to be able to afford this essential commodity. And we need our electric grid to be reliable and resilient in the face of climate change. So we know that reducing greenhouse gas emissions will require investments. It will change electricity demand and change the patterns of those demand. And we actually see similar changes when we think about adapting to climate change. There's also investments that will be needed in infrastructure, sometimes different types of investments than what we will need to reduce carbon emissions. We will also see higher electricity demand, not just from electrification, but also from increased air conditioning needs due to higher temperatures. And we'll also see changing patterns of hourly and seasonal electricity demand from changing weather patterns. So there's a lot of moving parts here. So just to summarize my remarks today, I hope I've demonstrated to you that the electric sector is pivotal to achieving our greenhouse gas reductions across every sector. It's also at the front lines of climate impacts. And as one of our colleagues remarked this morning, the electric sector is also potentially exacerbating some of those climate impacts that we're experiencing when the electric system ignites wildfires. So that risk goes both ways. The electric reliability is essential for human health. We see that with the health impacts, public safety impacts from heat waves, as well as extreme temperatures, cold and winter storms. So this is pretty essential. And considering climate impacts and decarbonization in that context of electric reliability is a key planning challenge. So what do we need? One thing that would be helpful would be research funding that could prioritize methods to jointly plan for climate risks, adaptation, and mitigation together. And I think that there's opportunities here actually that when we combine those research needs, when we combine climate mitigation and climate adaptation priorities, they may actually make each other more cost effective when we can consider and plan for them together rather than planning for them in silos. So with that, I will conclude my remarks. Thank you so much for your attention, and I look forward to your questions and any discussion. And I'll stop sharing for the moment here.
Thank you so much, Amber. That was a wonderful talk. Our first question of the evening, I'll encourage you all watching to please submit your questions again to our Q&A. It's open. Our first question of the evening says, I'm curious what you think about the role of investors and private sector owners in driving or obstructing adaptation in the power sector. How would you characterize their relative awareness and interest in climate information relative to folks in other sectors, such as the water sector, city planning, or others?
Yeah, that's a great question. It's interesting because the investors community is very diverse, and it's not at all unified in its perspective on these issues. But what I can say is that the ESG movement, the environmental social governance investing community, has grown massively over just the last decade. And so we see a large increase in the sophistication of the kinds of questions that we get from investors that are looking to, invest in development projects or invest in utilities, where they're really starting to ask more sophisticated questions around the long-term regulatory regime that utilities are going to be operating in. How is that going to affect their return, their bottom line? So I have seen the investor community starting to play a much more proactive role in calling for greenhouse gas reductions and also looking for opportunities to invest in companies that they see as being at the forefront of carbon emission reductions. The private sector, of course, is varied, but on the other side of that spectrum, we see coal generation asset owners looking for a rate of return on those assets. And so we need solutions for fossil fuel industries that have large potential for stranded costs. So I see it in both sides. In terms of relative awareness, I think there's in some ways been more focus on climate impacts in the electric sector than in other sectors. So I think the electric generation sector is a little bit ahead of this. The next frontier that we're starting to see is questions around, well, what about natural gas use in buildings? What about the industrial sector? So the conversation is starting to expand.
Our next question comes from Taylor Winchell, who asks, what are some examples, current or future, of overlap between mitigation and adaptation?
Sorry, what are some examples, current or future, of overlap between mitigation and adaptation? Yeah, so one example that I think is maybe most accessible that I think about is buildings, because we all live in buildings. And so you can think about constructing communities or building buildings that will be both climate safe and also adapting. And so an example of that would be designing the building for really good air quality, considering both indoor and outdoor air quality, taking into account the fact that there may be wildfires, for example, in the West. And that may also trigger the need to have a good, HVAC system that could be all electric. So avoiding the use of fossil fuels and getting air filtration at the same time. You can also design that building to be very energy efficient and also storm resilient. You can design that building to be more fire resistant with fire resistant roofs and drains. You can design that community to not be located in flood zones or not be located in wildfire zones, and think about locating it next to public transit and bikeable corridors. So I think, there's a lot of examples when you think about it in the building community. It gets a little bit more esoteric if we think about, the electricity sector. But I think there's examples there as well.
Yeah. Adam Levy asks, with respect to grid resilience, do you tend to value a more interconnected grid, high voltage DC lines, and bringing ERCOT into the other interconnections, or lean towards microgrid solutions in vulnerable areas?
Yeah, so this is a hard one. I think that it's the answer to, it's sort of the centralized solution versus the decentralized solution. And I think we're going to need to have a little bit of both depending on the context. So I think for communities need a safe space to where they can have access to power in the case of storms. And so that's a great use for microgrids. And that can be in places like, civic centers, hospitals, centers where we really need to preserve, public safety. Microgrids are very expensive. So I don't think that those are the solution that we want for the whole country. And there's sort of a risk of the wealthy departing from the system, because they can say, well, I can pay for a microgrid and assure my own electric reliability, so I'll be fine. While we undermine our equity and resiliency goals for the rest of the country. So we're going to need an expansion of transmission in order to develop renewable generation, decarbonize the grid, and build a more resilient, reliable grid, and then save those microgrids for the most pressing public safety use cases.
Yeah. Our next question is, can you reflect on optionality should the race to 100% clean power falter due to any of the numerous risks to implementing the transition to solar or wind? For example, investments in alternatives like nuclear, CCUS, direct air capture. Do you see any appetite by investors in these sorts of options? Should government provide support for them? So I know that's a lot of questions in one.
Yeah, no, I mean, it's asking about, how much do we put our eggs in one basket? And I think, we shouldn't. We know that wind and solar are the lowest cost options, and we can deploy them today, and we should be deploying them, as quickly as we can today. But even in the best case scenario, that's still only 70 to 90% of the generation mix, and so we're going to need alternatives. And I've been doing a lot of thinking and research about hydrogen. I'm pretty excited about that as a potential zero carbon source of generation. But I don't think we should take off the table the potential for innovation with small nuclear reactors. They're just, they're farther behind the cost curve and the development curve. So that's more an R&D priority than a massive deployment priority. And we're living in a world where we need to be deploying that zero carbon generation really quickly now, but without negating our R&D priorities.
Yeah. All right. What are your thoughts on the role of hydropower going forward, especially in the Western US?
Yeah, I mean, hydropower historically has played an essential role on the power grid before anybody was thinking about carbon emissions. And I think it's going to continue to do so. We know that climate impacts will reduce hydroelectric generation relative to historic levels. The latest numbers I saw on that was about a 10% reduction. So it's not that it's going away, but the seasonality of it may change. And I think what we are seeing is an interest in making that hydropower more sustainable. So I think there's opportunities to look at more forms of distributed hydropower, smaller scale that doesn't impact ecosystems, and it can be more fish friendly.
Yeah. And our next question, have you done any analysis of what the magnitude of change in electricity costs might be if we tried to reduce the risks of climate-related disruptions to zero while we were also decarbonizing? Are there any discussions in policy forums about how to address disproportionate impacts on low-income communities when the increase in costs is of this magnitude?
Yeah, so first I'll say that we never plan for zero disruptions. A typical planning standard, might be a 1 in 10 reliability event. So, one event every 10 years on average. And what does that actually mean in the context of climate change is a challenging and difficult question, but it would be exorbitantly expensive to plan for zero risks and zero outages. So it becomes a question of, how much risk are we willing to bear, and what are the trade-offs there? The electric sector cost increases from decarbonization. We have done some work and some estimates on those. And what's interesting is that to the extent that we are also increasing electricity demand as we decarbonize the grid, some of those costs can be spread out across more and more customers. So the cost impacts are, are not actually, I think they're not untenable, and they're uncertain, of course, but I don't, we haven't seen this to be, as bad as the naysayers were fearing. When I started working on electric decarbonization a decade ago, in California, they had just set a goal of getting to 33% renewables by 2020. And now the state is at 60% renewables by 2030. And there was a lot of hand-wringing that 33% renewable target was going to be far too expensive and break the grid. And that hasn't turned out to be true, because the cost of solar in particular has come down a lot faster than anyone expected. And the cost of natural gas is actually dropped by something like 5x relative to what it was in the early 2000s. So both of those factors have helped actually reduce some of the upward pressure on electric rates that we would otherwise see. Not to say we're out of the woods, the wildfire costs and that we're seeing, in PG&E service territory in particular here in California, are pretty big. But as long as the electric grid and electric demand continues to expand, again, those costs can be spread around and reduce some of the customer cost impacts.
Our next question comes from Naomi. What do you think is the likelihood of changes in policy at the federal level that would make it easier to build long distance transmission?
Yeah, that's a good question. It's a topic that the feds have tried to tackle before, and it kind of goes back to the point I was making about the distributed governance structure of the electric sector. In many ways, at least still today, the permitting and the decisions around transmission siting is still very much a local issue. I think it would be challenging to change that dynamic in our country today.
I'd ask a follow-up question to that out of personal curiosity, what have you found as, given that it'll remain a local decision for the most part, what have been some of the most successful approaches to navigate when new transmission does need to be built or replaced?
Yeah, that's a hard one, Emily. I don't know if I have the answer to that.
No, that's okay.
I mean, I think there's a lot of smart people and companies that are working on this, and it starts by having a really smart plan for siting, and that that includes avoiding sensitive ecosystems and sensitive view sheds is probably the number one. Is really comes down to the details of where are you putting it.
For sure. We have a couple upvoted questions from this one from Oriana. If you could wave your magic wand and suddenly have any future climate information to support future energy planning, what would that information be?
Oh, great. Well, a near-term piece that we're working on is, I don't think too far out of reach, so maybe I don't need a magic wand for this one, but having that hourly resolution on correlated solar, wind, and loads in a climate future. Like that's sort of the that's what we need right now that we don't have. You know, there's pieces of it, but putting it all together so that it's a coherent data set that can be used for planning purposes, to my knowledge, doesn't exist. More longer term things that I would love to understand is you know, how is climate change going to impact, you know, how and where people want to live? Are we going to continue to you know, live in flood prone and wildfire prone regions as the impacts, you know, become more and more severe? All indicators today would point towards yes. We're going to live where we want to live, and we better figure out how to make that safe. So that's not really a climate data question, but it's a population data question.
Well, it'd certainly be a game changer. Yeah, I know that living in a fire-prone area, it's one that I grapple with personally as well. Another upvoted question we have: are you concerned about the over-reliance on offsets in net zero planning?
So offsets, people mean different things when they talk about offsets. When we think about an economy-wide net zero emission reduction scenario, there is no offset anymore. It's either it's a carbon reduction or it's a carbon sequestration, or it's not. There's, I think, certainly regulatory or kind of governance challenges around verification of carbon sequestration in forests and soils or in CCS. And that is something I'm concerned about. I think we need to do some more work to improve our monitoring and verification of those carbon sinks.
For sure.
But I don't think they're offsets anymore in that context. They're carbon sinks. In a kind of a cap and trade world framework where you're thinking about, you know, direct emission reductions and then you know, buying credits from other markets, I think there's a very wide range of quality of those offsets, and some of them are very rigorous and well verified, and some are not. So that's a buyer beware kind of a situation.
Great. Maybe we'll ask one more question or two. Another one from Andy: what are your thoughts on considering indirect impacts of climate change on the electricity grid? For instance, you mentioned impacts of climate change on where we live. What about heavy reliance on desalination or groundwater pumping for water sector adaptation, et cetera?
Yeah, I mean, it's a good point. We will, you know, we actually, in some of our carbon scenario work in California, we ended up modeling electric loads from desalination for a few plants along the coast that have been proposed, not all of which have been built. You know, and those didn't actually end up moving the needle very much. You know, even though individually in an individual community, it's a relatively, you know, large electric load. From a California-wide perspective, it didn't really change much. It didn't show up in the figures. But that's not to say there aren't other examples that will end up being much more impactful. You know, the one that's most obvious or salient to me is just air conditioner saturation. And, you know, when we saw the heat wave hit the Pacific Northwest and everybody runs to the store and buys their window unit AC, starts plugging it in, and, you know, those are not efficient units. That's going to really lead to a big increase in electricity demand and changes to this peak period as well. So air conditioner saturation in places that haven't historically needed it, including places like the Bay Area, I think that's the big one.
Yeah. This question from Bart Nyssen: transmission constraints are a big challenge in electrifying our energy needs using weather-driven renewables. What innovative plans have you seen to address these transmission bottlenecks? And I'll have that be our last question for the evening.
Oh, innovative plans to address transmission bottlenecks. You know, some of the biggest improvements in transmission constraints that we've seen have actually come from changing the ratings on the existing lines.
Mm-hmm.
And that's a little bit of a fine point, but it's actually really important, because the way we plan our transmission grid is largely built on a 50-year-old set of heuristics that were designed in a world where you had, thermal generators in certain locations and loads in other locations. And what we're finding is that in some cases, you can actually increase the line rating on these transmission lines, without upgrading it. So existing transmission corridors and improving the existing lines, I think, is a really promising direction. It won't solve everything, but it certainly helps move us in the right direction.
Yeah. Well, thank you so much, Amber. You've been just a wealth of information. This has been incredibly informative. I'd like to thank you. And since no one else can be heard, I will clap on everyone else's
I wish
behalf.
I could see you all.
Yeah. Thanks again for joining us tonight, everyone. A recording of this public lecture will be made available on AGCI's website at agci.org within the week. And thanks all for joining. Bye for now.
Thank you.